Today we are going to define a sequence and utilize summation notation. So a sequence, or an infinite sequence, is any function whose domain is the set of positive integers. Sequences whose domains consist only of the first n positive integers are called finite sequences. So it means that there's a limited number of terms, because each number in the sequence is called a term. And we label them using subscripts. So A1, A2, A3, A4, A5, AN. We could also use T. Sometimes you'll see T1, T2, T3, T4, up to some set number. So Tn. So let's take a look at our first sequence. There's a typo here. This should say in the sequence. We have 1, 1, 2, 3, 5, 8, 13, 21. So the first term is this one, so it's A1. The second term is A2. The third term is A3. The number 3 is term 4 because it's fourth in line. The number 5 is term 5. The number 8 is term 6, and so on and so forth. So we would say that A1 is 1, A3 is 2, just so we understand how terms are labeled. And we want to find A11. So we have 8 terms here. And the way that you find these terms is by adding the 2 terms before it. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 2 plus 3, 8 is 3 plus 5, and so on and so forth. So we can't just go get A11. We have to do some other work. We need to find A9, A10, and then we can find A11. A9 would be 13 plus 21, so that's 34. A10 is 21 plus 34, or 65. And then A11 would be 34 plus 65, which makes it 89. Most terms in sequences are a little bit easier to find because we're normally given what's called an explicit definition. So if we look at the first example, this is an explicit definition because if I plug 1 or 2 or 3 in for my term number, then I can get out the value. So A1 is equal to 2 times 1 plus 5. A2 is equal to 2 times 2 plus 5. A3 is equal to 2 times 3 plus 5. And A4 is equal to 2 times 4 plus 5. And then we want to actually get the numbers in the sequence. So we'll do the math. 7, 9, 11, and 13. So our sequence is 7, 9, 11, 13, and it may go on forever, but we were only asked to find the first 4 terms. We can do that again with example number 2, and again it's an explicit definition because we can just plug in the value for our term number. So A1 is negative 1 to the 1 over 2 to the first plus 1. A2 is negative 1 to the second over 2 squared plus 1. We'll get values for those in a moment. A3 is negative 1 to the third over 2 to the third plus 1. And A4 is negative 1 to the fourth over 2 to the fourth plus 1. The actual values for these are negative 1/3, positive 1/5, negative 1/7, and, 1/9, and positive 1/17. When we look at example 3, we can see that it looks a little bit different than the other two examples because we're given our first term and we have a definition where we have this a sub n minus 1, which means the term before it. So before we look at this kind of problem, we'll actually go on to 4. And 4 is again explicit because we can just plug the term number to get into a formula to get the term value. So a1 is the sine of 1 pi over 3. a2 is the sine of 2 pi over 3. a3 is the sine of 3 pi over 3, also known as pi. And a4 is the sine of 4 pi over 3. And then we evaluate that. Sine of pi over 3 is root 3 over 2. Sine of 2 pi over 3 is root 3 over 2. Sine of pi is 0. And the sine of 4 pi over 3 is negative root 3 over 2. So now let's go back and take a look at example 3. And here we see that things are a little bit different, and so we need to address the fact that we'll start with our first term of 3. We're just given that value in the definition. We can see it right here. But what's going to happen is that a2 is going to equal 2 times a1 plus 5. Well, we know that a1 is 3, so a2 is 2 times 3 plus 5, or 11. a3 is 2 times a2 plus 5. Well, we know that a2 is 11, so 2 times 11 plus 5 is 27. And then a4 is 2 times a3 plus 5, which is 59. Example number 3 is an example of a recursion formula, or a recursive definition, and it defines the nth term of the sequence as a function of the previous term. So what will always happen is that you'll have an a sub n equal to a sub n minus 1 with some operations performed on your a sub n minus 1. So plus some stuff, maybe we'll multiply by some stuff over here. Because you can't find the next term without the previous term, you have to always define the first term, okay? So that's one of the keys, is that you must always define the first term. All right, moving on to the next page, we can actually enter these into the calculator. The first thing you need to make sure is that when you're in your calculator, you go to the mode button right here, and you highlight the words SEQ. Okay, that means that it'll be 4 sequences. Once you do that, putting in explicit formulas is very straightforward. You'll have a menu when you look at y equals right here. You'll press that button, and this is the screen that will pop up. All right, and the n-min will be there because we're starting with the first term. Then if we were to do example number 1, we would literally just type in 2n plus 5. So you know where the 2 button is. The n button is where you would find the x button if this were a y equals mx plus b or some kind of polynomial, and then plus 5. And then you can see all of your values by hitting second and the table button. And that'll give you a table with n, and then the calculator calls it u of n. And so you would see 1, 2, 3, 4, and just like we found previously, it would be 7, 9, 11, and 13. So using the calculator is a nice way to check that you've done your arithmetic correctly, and also that you didn't make any kind of computational mistakes. The one thing you need to be careful of is that it will turn fractions into decimals. So, for example, number 2, it's somewhat difficult to know what 1/17 is as a fraction or as a decimal. Recursive formulas are a little bit more challenging, but still fairly straightforward. So the recursive definition that we had on the first page was that a sub n was equal to 2a sub n minus 1 plus 5. The calculator turns the a of n or a of n minus 1 into a function. You can see the function notation right here. So we're just going to have to tell it in function notation. So we'll put the 2 in. The U button is right here. You can see the little U right there. So you hit the second button and then the 7, and that'll give you the U. You'll put a parenthesis, and then the N is still where the X is. You'll close that out, then type in plus 5. The one thing that you have to be careful of is that in our recursive definition, we always have that first term, A1 equals 3. So you have to enter the first term where it says U n min. That'll be your first term. And you need to put these curly brackets in, which you find over your normal parenthesis. So you'll enter the curly bracket, you'll enter the 3, you'll enter the other curly bracket, and then you'll be able to go to your table by hitting second and the graph button to check that you did everything correctly. So now that we have a way to check some of our work with a calculator, we're actually going to shift gears and do something that involves no calculators, of course. So we are going to introduce factorial notation. Factorial notation has its own special symbol. So it is the exclamation point. All right, it's read n factorial. And so n's a positive integer, and n factorial is the product of all of the positive integers from n down through 1. So you can see that n factorial is n times n minus 1 times n minus 2 times n minus 3 until you get down to 2 and 1. So if we were going to do 6 factorial, it's equal to 6 times 5 times 4 times 3 times 2 times 1. And then we just need to know this one rule, that 0 factorial is 1. And now we can do some examples with the factorial notation. So in our first example, we want to find the first 4 terms of the sequence that's defined by that. Yay, we have an explicit definition, so we can just plug it in, our term number. So A1 is 20 divided by 1 plus 1 factorial. A2 is 20 over 2 plus 1 factorial. A3 is 20 divided by 3 plus 1 factorial. And A4 is 20 over 4 plus 1 factorial. So now we'll do some computation. We'll have 20 over 2 factorial, which is 20 divided by 2 times 1, which is 10. This is going to be 20 over 3 factorial, which is 20, and 3 factorial is 3 times 2 times 1. So 20 over 6, which reduces to 10 thirds. Then we have 20 over 4 factorial. So 4 factorial is 4 times 3 times 2 times 1, which is, 12, 24. So 20 over 24, which is 5, 6. And then 20 over 5 factorial. And the 5 factorial is 5 times 4 times 3 times 2 times 1. The 5 and the 4 would cross out with the 20, and you'd be left with 1/6. Okay, so getting a little bit more practice with the factorial notation, we'll evaluate these without a calculator. 14 factorial is 14 times 13 times 12 times 11 times ... all the way down to 1. 2 factorial is 2 times 1. And 12 factorial is 12 times 11 times 10 times ... So the nice thing that you may notice is that the 12s will cancel with the 12s, the 11s will cancel with the 11s, the 10s, and all of this stuff down there. And so then we're just left with 14 times 13 over 2 times 1. And we can cross out the common factor of 2. 2 goes into 14 7 times. And so we're really left with 7 times 13, which is 91. Looking at the next example, it's algebraic. So n factorial is n times n minus 1 times n minus 2, and again, all the way down to 3, 2, and 1. N minus 1 factorial, we'll start with n minus 1, then n minus 2, then all the way down. And so again, you'll see that we have these common factors in the numerator and the denominator that we can cross out. And so this simplifies to just n. There's one more bit of notation that we're going to need as we work through sequences and series in this unit, and that's the summation notation. So summation notation is the sum of the first n terms of a sequence, and it's represented by this epsilon. And so we say that we start counting at 1, we go up to whatever term number it is, and then it's term 1 plus term 2 plus term 3 plus term 4, all the way up to term n. I is called the index, and n is the upper limit, and then 1 is the lower limit. These limits are just where we start counting, or where we stop counting. So let's blow this up a little bit and take a look at some examples. We'll do these without our calculator. So for the first example, we have the sum from I equals 1 to 6 of 2i squared. So we're literally going to put the 1 in and substitute. So we'll do 2 times 1 squared plus, these are the term numbers, so then the second term, we'll put a 2 in, and that's 2 squared. Then 2 times 3 squared plus 2 times 4 squared plus 2 times 5 squared plus 2 times 6 squared. Each of these individual expressions, this is a 1, this is a 2, this is a 3, so these would be the numbers in the sequence, but now we're being asked to add them all together. So we'll just go ahead and start doing some evaluations. So 1 squared is 1, times 2 is 2, plus, this turns into 8, 18, 32, 50, and 72. And then we need to add these all up. 18 plus 32 is 50, plus another 50, 100, 172, 180, 182. So we should get 182. For our next example, we are given the summation, I'll scroll over for us, from k equals 3 to 5 of 2 to the k minus 3. So what I want you to realize is that I doesn't always have to be the index. You can use a different variable, and that you don't always have to start counting at 1. You can start counting at 3, but you still have to count with integers. So again, we will go ahead and just substitute in. So 2 to the third minus 3 is the first term, plus 2 to the fourth minus 3, plus 2 to the fifth minus 3. 2 to the third is 8, 2 to the fourth is 16, 2 to the 5th is 32. If we add these up and subtract off the 3's, we end up with 47. Oops. 2 more examples for the summation notation before we try and go in the other direction. So in this example, where we go back to an index with of I and a lower limit of 1. Our upper limit's 5, and we're just given a 4. There's nowhere to substitute the I value, so we literally just write 4 down for the first term, and 4 for the second term, and 4 for the third term, 4 for the fourth term, and 4 for the fifth term, because we stopped at 5. And if we add 5 4's together, we get 20. Okay, in this example, our summation looks a little bit different because the k is next to the epsilon as opposed to below it. That's just a function of the program that I use to type it in. So it doesn't mean anything different. We'll start counting at 1, we'll stop counting at 6. And we'll just substitute in. So cosine of 1 pi over 4 plus the cosine of 2 pi over 4 plus the cosine of 3 pi over 4 plus the cosine of 4 pi over 4 plus the cosine of 5 pi over 4 plus the cosine of 6 pi over 4. Whew, now we get to evaluate it. The cosine of pi over 4 is root 2 over 2. The cosine of 2 pi over 4 is really the same as the cosine of pi over 2, which is 0. The cosine of 3 pi over 4 is in the second quadrant, so it's negative root 2 over 2. Cosine of 4 pi over 4 is the same as the cosine of pi, so that is negative 1. Cosine of 5 pi over 4 is negative root 2 over 2. And the cosine of 6 pi over 4 is the same as the cosine of 3 over 2, so that's 0. And then when we collect up and combine like terms, we're left with negative 1 minus root 2 over 2. And we can just leave our answer like that. We don't have to find a common denominator. Okay, so now that we're feeling a little more comfortable, hopefully, with evaluating summations, we're going to write series or sums in the summation notation. So the hint that I always give students is to write the term number above it. So this is A1, this is A2, and this is A3, and this is A something. And then let's see how the term number 1 is connected to 1, or 2 is connected to 4, 3 is connected to 9. And what I hope you're realizing is that each of these terms is the square of the term number. So 1 is 1 squared, 4 is 2 squared, 9 is 3 squared. So if we were to continue that, 196 would be 14 squared, which means that we have 14 terms. So then we can use our summation notation. We'll start counting at 1. We'll stop counting at 14 because we have 14 terms. And we said that we get the term number the term value by squaring the term number. So we write that as I squared because I is the term number. In our next example, let me scroll over, we have this sequence and the sum of these terms. So we'll go ahead, write A1, A2, A3, A4, and we get down here and we see that they've actually given us an expression. The question is this AN or AN minus 1? And we know that since 1 is really 2 over 0, this whole term is actually our expression. So this is AN. So we're going to count from 1 to n, and then they told us how to find it, 2 to the n minus 1. And that's it. All right, let me know if you have any questions.